And you could look this answer up in Slater or Topper or Course Hero or online, and you could be done with this in 5 minutes. But you would also pretty much learn nothing if you did that. There'd be almost no residual benefit. Yeah, you get a few good points for the quiz, but you'd be more than making up for it with the points you'd lose on the exam, unless you learn it, unless you engage in some deep learning here. All right, so this is a loaded penguin sled. A penguin in a box on a ramp. All right, what I did over here, I just redrew this a little bit bigger so we can get a better visual. All right, loaded penguin sled. We know the mass of it. And now we're not ignoring friction. The difference between chapter 5 and chapter 6 is this. In chapter 6, we do care about kinetic friction and static friction, and we do care about centripetal force, which means centripetal acceleration.
Hey, real quick, my chapter 6 question 1 is it's about 2 cars sliding down a hill, not a penguin.
Yeah, Professor, yours says chapter 6 problem, problem 16, but
sure Levi, once again, I think that was Will talking. I can't hear you, Will. But your chapter 6 quiz 1 is looking like this. Let me see. It's looking like this, probably, right?
Yes.
Yeah.
All right. Let me do this then. Chapter 6 quiz 1. Let me fix it then. It'll be easier if I do this. So give me a minute. Let me actually. So apologies for the inconvenience and the delay, but let me just go in and fix it the right way. All right. This is 13, so I can do this. Give me 1 minute. Chapter 6 quiz 1. All right. So I need to make that 16. All right. If you go all the way out and come all the way in, and if you go all the way out and come all the way in again, you should see this problem. So again, I'll be able to fix that going forward. This should be the only time that mess up happens, but thanks for letting me know. Okay, so let's jump into it. Penguin. This is a job. So it basically says, let's look at part A. I mean, we have a whole bunch of givens, but at the end of the day, this is what we need to do. What is the minimum magnitude of the force F parallel to the plane that will prevent the sled from slipping down the plane? All right. And this is a good first problem. This is a good first problem for chapter 6 because there's a lot of nuance here. There's a lot going on. And I'll just say right now, because this involves forces, this is definitely a job for the force analysis method. So that's why I'm saying chapter 6, deep diving into chapter 6 is going to really help you with chapter 5 because it's very, there's a lot of reinforcement that goes in. So at this point, you guys should know, again, I'll provide it on Thursday, but you should know that the force analysis method means, yes, you got to do a free body diagram, one free body diagram for each body, because sometimes you have 2 or 3 or 4 bodies. You need to think hard about a coordinate system. You need to do decomposition. And then after decomposition, you're doing the X force inventory and or the Y force inventory. And right after an inventory statement, you say something about acceleration, and then you just keep repeating and then crunch. Okay, so at this point, I'd be kind of a little bit surprised if you don't have this memorized. free body diagram, coordinate system, decompose all 2D vectors, do the inventories, make a statement about acceleration, and then crunch. And then you repeat it. You basically keep repeating this over and over again until you get enough equations, until you get enough equations to solve. And getting enough equations just means you're binding the system. You're actually defining the system. What does an equation do? What does an equation in physics really do, or math for that matter? It basically bounds the system. Because every equation says, well, whatever else is going on, this has to be true. And if you get, so this is an equation, and then this is an equation, and then this is an equation. And if you get enough equations, you know that
I think you're on the wrong screen.
Oh, geez. Okay. Yeah, feel free to speak up. You guys, if it seems like I'm talking off screen, feel free to speak up sooner as opposed to later. Not that it's your fault, but it was my fault. All right, so let me not repeat everything. You don't have to memorize this, but again, I would be surprised if you don't have number 1, 2, 3, 4, 5, 6. I would be surprised if by now the amount of time you've spent on the homework, and again, it's unusual to not get full credit on every homework assignment. That's a red flag. But you need to know this. You should really know all of this. Okay, so let's go into it now. It says, what is the minimum magnitude of the force that will prevent the sleds from sliding down the ramp? So step number 1, free body diagram. You know that's where it begins. So let me just clear the room here. Here comes the free body diagram. I have one of those forces shown. So here's the weight force. Weight typically acts on the center of mass. Let me get it different. The weight force typically acts on the center of mass. So this is what the weight force looks like. There's the center of mass, or I'm sort of saying there's where my center of mass, maybe a big dot to indicate the center of mass is right there. Okay. That's one. So now I'm showing 2 forces. Here's another force. Another force is the normal force. The normal force is the Newton's third law reaction force that acts perpendicular to the shared boundary between the 2 objects. And if what I said sounds weird to you, that would be a little bit perplexing to me, because this was hammered heavily on the green sheets and in the lecture video. So the term normal is a mathematical term, which means at a right angle to. So here is the right angle. This normal force is basically the force from the ramp pressing up on the body that we're examining. And it's always perpendicular to the shared contact surface. So I'm indicating that here in this highlighter. That this blue line is the shared contact surface between these 2 objects. The normal force is perpendicular. So that's a good visual. But wait, there's more. There's friction. We're not ignoring friction. And then here's where things get really kind of thought-provoking. All right, so I'm not going to ignore friction like I did in chapter 5. But what am I going to do with friction? Here are my choices. Am I going to deal with kinetic friction or static friction? And then once I figure out, is it kinetic friction or static friction, and then I have to worry about the direction. So this is like a inflection. This is a key point. Do I worry about kinetic friction? Do I worry about static friction? And then what's the direction? And then this is where you have to read the question. Again, part A, another read through for part A. This is the secret sauce in solving problems, is reading the question like umpteen times. What is the minimum magnitude of the force F parallel to the plane that will prevent the sled from slipping down? So I'm just going to read that over and over, slipping down. So, geez, this is pretty thought-provoking. Do I need to add a kinetic friction vector, or should I add a static friction vector, or maybe both? And then what's the direction? So here's my thought process. Well, if I'm pushing up on the penguin box, here's my goal. I want to start reducing my force F. I want to start reducing this force so that I just have the bare minimum force that prevents the sled from slipping down the plane. So this is my thought process. And I'm thinking, here's another breakthrough. I'm thinking the following. Maybe I'll start here. For part A, in this case, static friction helps me prevent penguin from sliding down ramp. And again, that's my thought process. I'm applying more than enough force than I need. So I'm going to back off. I'm going to diminish this force right here so that it, along with static friction, will prevent the penguin from sliding down the ramp. In this case, static friction helps me prevent penguin from sliding down the ramp, from moving, I'll just say, from moving, because it says will prevent the sled from slipping. All right, so the penguin is sitting there at rest. So this is what I'm going to do with friction. Friction is another force, and it's up the ramp. So to me, this is the most strenuous bit of thinking thus far. And I want to really make sure, okay, if I need to minimize this force as much as possible. I want to minimize it to the point where I am just barely able to combine with the static friction force to prevent the box from moving up the ramp or down the ramp. So it's that break even I'm using for, that I'm looking for. I'm looking for that break even threshold force. So I just got to solve for this. All right. So I am done with the free body diagram. Next, what's after free body diagram? Coordinate system. Here's what I'm going to do for my coordinate system. And remember, this is so important. I'm going to write it down. Here's the coordinate system how to. Set coordinate system axes, plural of axis, in direction of acceleration. That's and make all coordinate systems flow together. Because you might have, if you have two bodies, you have two coordinate systems. If you have three bodies, you have three coordinate systems. However many coordinate systems you have, make them all flow together. So that is your how-to in terms of selecting a coordinate system. So given that, I don't know. Well, technically speaking, there's no acceleration here. So, but I do know one thing. I know the penguin is going to accelerate either up the ramp or down the ramp if there was an acceleration. So you know what? That does force my hand. I'm going to call this plus y, and I'm going to call this plus x, because I know one thing about x. The penguin, if there was acceleration, the acceleration would be parallel or lined up with this ramp. And if that's plus x, this is going to be plus y, because x and y are always perpendicular there. So that's my thought process. We're done with the coordinate system. Now we have to decompose vectors. So just staying committed to force analysis method, which you guys as future engineers and scientists, you love this. You must, or you will come to love methodology, rational methodology. So let's do the decomposition. All right, so here's me decomposing the one and only two. I only have one two-dimensional vector. It's the weight. All right, so there's the, this is the y component, and this is the x component. And I know y and x are always perpendicular, which does make life easy because that means I get to use right angle trigonometry. I'm just doing some fine tuning here to make it look aesthetically pleasing. So this is my right angle. Right angle. Good. I better label this. This would be MGY. This is MGX. And this is MG because we know that weight equals MG. So weight equals MG decomposes. This is the y component. So this is y because this is parallel with the y-axis. And this is MGX because this MGX vector right here is parallel with the x-axis, right? Like right here. Okay. So I am done with the decomposition. You might remember, I'm just going to go through this quick little angle game. Like if this is theta. So for the sake of conversation, I'm just going to say, what if this theta is 20 degrees? I'm just going to make up a number that's easy, simple. If that's 20 degrees, well, I know this angle is 90 degrees. Let me move this. So I'm just going to go through this sort of like backdoor method, this reverse engineering method to get the triangle angle. I know that this is 90 degrees. Okay. So again, to play the game, if this is 20 degrees, if this is 90 degrees, this must be 70 degrees right here. And if that's 70 degrees, I know for a fact that that's 90 degrees because this MGY vector is perpendicular to that surface. So if that's 70, this is 20. So this is my approach to say, well, if this is 20 degrees, then this is 20. If this is theta, that's theta. And the only reason I'm going through it again, because right now it's always the same kind of ramp. It's always the same kind of layout, but it's not always going to be that way. So I'm just giving you a methodology that works for me. Maybe it works for you in terms of finding the triangle angle based on the ramp angle. So once again, if my ramp angle is theta, based on my ingenious approach, I can figure out, or I know that this is also theta. Okay. So done with decomposition. What's next? What's next is the X force inventory and or the Y force inventory. So step number 2, let's go with the X force inventory. X force inventory, in this case, says the sum of all X forces acting on the body, and the body is the penguin. There's only one body here. You might say there's 2 bodies, but there's only one body that's in scope for us, and that's the penguin in a box. So I have negative MGX because MGX, as you can see from my visual, MGX is trying to pull the penguin down the ramp. Yes. Anything else? Yes, there is something else. Plus FS. FS is trying to keep the penguin motionless along with F. So speaking of F plus F, that's it. That's it. This is my inventory. This is my force inventory. All of those forces, negative MGX plus FS plus F, all of those forces collectively will produce this acceleration, mass times A sub X. Okay. So, and it does make sense. I mean, all this is just a formalized way to crank out F equals ma. There's a force going in the negative direction. Here's a force going in the positive direction, along with this force going in the positive direction. Whatever they net out to be, it equals ma, thanks to Newton's second law. The very next thing I have to do is say something about acceleration. So step 3, you got to say something about acceleration. And what I'm going to say is the following: A sub X equals 0 since penguin is motionless. Penguin must remain motionless. So that's what I can say about acceleration, which is important. So let's keep going. Let's just keep processing this. here goes, negative mg sine theta plus mu subscript sfn plus f equal 0. So where did number 4 come from? If I look at this triangle here, I would say, because it's a right angle triangle, sine of theta equals side opposite over hypotenuse. So sine of theta equals mgx over hypotenuse, which is mg. So that's how I do this substitution. mgx does equal mg sine theta. Let me fix this. mgx does equal mg sine theta. Fine. So that's where this comes from. So now you know where that comes from. This, you should know this. You've had way more than enough time to finish your green sheets. And by the way, I'll come back to that in a minute. But you do have the green sheets finished. You do have the video digested. This was one of the introductions. Static friction is defined as mu sub s times f sub n, and everything has a name. This is called the coefficient of static friction. It's a stickiness factor. This is a material property. This is the coefficient of static friction. So, for example, what do you think is stickier, a sheet of rubber or a sheet of ice? Obviously, a sheet of rubber is more sticky, so it has a greater stickiness factor. This is normal force, which is staring right at us in our free body diagram. So this was explained up, I think, almost an entire page and lots of minutes were dedicated to static friction and kinetic friction. So that is for sure worthy of your time to digest. Okay, so now what? Now I guess we solve for F. All right, number 5. Solve for F, number 6. F equals mg sine theta minus mu sub s. Again, that's mu. This is Greek letter mu, which you print. It's Greek letter mu. That's how you spell it. This is how you pronounce it. Mu, like Mewtwo from Pokemon. It's not you. It's mu. And the S means static friction. Okay, so I guess we're done. Let's do step 7, or let's solve for F, because we know everything here. Well, you can say, wait a minute, Chris, stop the presses. You don't know the mass of this, but I don't know mass, but I do know mg. Mg is the weight. So I don't know m, but I do know mg. And the problem says, for me, the weight is 70 newtons. And I got to fix this little typo here. This should be mu sub, and just when you think we were clear, we're not done, because now I have a giant, this should be F sub n. And then this is where I write down, what's F sub n? F sub n is unknown at this point. So let's go to step 7. So I'm basically out of gas. This is what I have right here. This is my end state for my X force inventory. And I was feeling pretty good until I encountered that F sub n. But you should know by now, it's just a matter of cranking out another formula. And that's what I was saying before. If you crank out enough formulas, you combine them to sort of draw a boundary. So now that you're actually looking at my screen, because I forgot to share it before, this is what I was saying. Like here's an equation, here's an equation, here's an equation, and here's an equation. So your solution to whatever problem you're dealing with is somewhere within this bounded region, where every one of those lines represents an equation. So anyway, let's do a Y force inventory, step 6, step 7. Maybe maybe a Y force inventory will produces provides Fn. Maybe, I hope so. Right now, this is the only idea I have. If this doesn't work, I'll think of something else. So number 8, let's do a Y force inventory for the same system, which means the sum of all Y forces, and this is where you have to stay committed to your free body diagram. I've got normal force going straight up, and you could say, hey, Chris, this isn't straight up, but it is straight up in our new coordinate system, minus mgy going straight down, and then that's it. So I don't have 3 forces, I only have 2, and Newton's second law says whatever those forces turn out to be and how they blend together, it's mass times acceleration, and then you have to say something about acceleration. And in this case, I can say a sub y equals 0 because there is no plus or minus y motion. This penguin, even if the penguin were moving along the ramp, there would still be no plus or minus y motion because the penguin stays on the ramp, which means its y position never increases or decreases because of our new and improved coordinate system. So step 10 leads us to the following. I can say F sub n equals mgy, and ultimately F sub n equals mg cos theta. So again, just looking at this triangle one more time, if I look at this triangle, cosine of theta equals side adjacent, which is mgy all over hypotenuse, which is why I'm saying mgy equals mg cos theta. So there you go. Now I have reached the end of the line as far as my Y force inventory. Alrighty then. You now have an X force inventory result, and you now have a Y force inventory result. Go ahead and solve for F. And that's just part A, and then we'll do part B. Let's all get the answer to part A using step 6 and step 7. I'll say this, find F from number 6 and number 7. Okay. And when I do that, $70 times sine of 19 minus mu sub s. Again, mu sub s is the stickiness factor. How sticky is that ramp? It's sticky to the tune of 0.28 times 70 times cosine. Okay. .257 newtons. This is the answer to part A. We are completely done with part A. Part B and C are going to be equally thought-provoking. We can probably move faster because I'm introducing a lot of the basics now. They have just been introduced. Let's see how people are doing on part A. This is chapter 6, quiz 1. Okay, a few people have got part A. And when I say a few, I mean 2. So
I'm sorry, I don't know what to do with after I have the normal force. I know I need to go to 6. I have the normal force. I don't know what to do next. I know you said go to 6 and 7, but I'm still seeing 2 unknowns.
Yes. So look at equation. Let's look at equation 6. Equation 6. Do you know mass. No, you don't know mass. You don't, but you do know mg. So you collectively, you know mg. For me, it's 70 newtons because it was given. Do you know theta? Yes. For me, theta is 19 degrees. Do you know mu sub s? Yes, mu sub s is given. That's the stickiness factor, also known as coefficient of static friction. Do you know F sub s? No. F sub n, I should say. No, you don't know F sub n, but you do know F sub n because F sub n is in reality this. So again, you do know mg, yes, and you do know theta. So that's why you can get your answer. This is, I mean, to be honest, just in case anyone else is in this boat, you need to be really comfortable with this algebra. And the only way if you're not comfortable now, the only way you're going to get comfortable is literally hours per day practicing. Not hours 2 or 3, like hours per day practicing. That's, I mean, just being straight up honest with you. If you don't know this kind of algebra, you definitely know what you need to do. And that's like hours per day, 5 days a week, 5 out of 7 days a week doing physics, because that's the only way you're going to start to feel comfortable with this algebra. All right. So let's see how people are doing now. That's the insidious thing. You learn that algebra in 9th grade. And the problem is if you haven't done it since 9th grade, and if you're like me, you're going to be rusty. And the only way to remove rust is to time. There's no nifty shortcut. All right, let's move on. Because again, I think we maybe have, if at this point, you guys, and this is just meant to be helpful, if at this point you don't have the right answer, it means you're getting stuck by 9th grade algebra. And I don't say that with any sort of abrasiveness. It just means you need to, Thursday is 2 days away. You need to be really proficient in algebra. And that happens just through sheer number of hours and staying away from looking up the answer. All right, so let's do part B. Part B. So part B is saying the same thing, except with one difference. Part B is saying, what is the minimum F again? So once again, we're after the minimum F. However, check out what part B is saying. That will start the sled moving up the plane. So I'm going to clear my free body. Well, I'm going to clear some of my free body diagram. Because now instead of finding the minimum F that prevents the sled from slipping down the plane, now the challenge is finding the minimum F that just barely starts the sled moving up the plane. So we're looking again for this breakthrough, this sort of break even F. So let me get rid of some stuff here because we can reuse. Now, if this were an exam, you would just draw a completely new free body diagram, which is fair. I'm just going to recycle this. All of this trig stuff remains true. So I'm just going to get rid of that because that doesn't change. Sine theta equals mgx over mg doesn't change, et cetera, et cetera. So I'm just going to focus on the stuff that changes. There's one and only one vector that changes here. So I'm going to get rid of f sub s. And as I read part B, and I'm going to read it again, that's the secret. Part B says, what is the minimum F that will start the sled moving up the plane? So I'm still back in this mode right here. I'm asking myself, do I need to worry about kinetic friction or do I need to worry about static friction? And what about direction? So when I read this, I'm saying this is my internal dialogue. I'm reading part B. You can see it on your screen probably easier than you can see it on mine. What is the minimum F that will just start the sled moving up the plane? So let me go to step over here. Step 10. For part B, F min works against the static friction force and this component of gravity. All right, so let's just talk about what's trying to pull this box down. What's trying to pull this box down? MGX. MGX is trying to pull this box down. Okay. What else is trying to pull this box down? Well, think about it like this. I'm applying some force. I'm applying this force right here, this F force. And my goal is just to keep growing the force. I'm going to keep increasing the force until I get movement. So before I reach that point, before I reach that magical force value, I am fighting MGX, which is trying to drag me down, and static friction. Think about it like this. I'm trying to exert. So this is me. I am trying to push the box up the ramp. And what does static friction do? Static friction tries to resist a change in motion. So this is what static friction looks like that. That's static friction. So this is literally the conversation that's going on in my head. Just saying it out loud. But this is up the ramp. So again, remember the role of static friction. Static friction, F sub S, static friction tries to keep everything motionless. That's what static friction does. And then at some point, you might be able to beat static friction and you're going to get slippage. But static friction, F sub S, tries to keep everything motionless. So that's how I'm getting this free body diagram. Everything is the same except for I have a static friction vector pointing down the ramp. So it's business as usual. Let's do a new X force inventory. The Y force inventory is going to remain unchanged because nothing changed in the Y dimension. So this is going to be the only new inventory. I've got minus FS minus MGX plus F equals mass times acceleration. Okay. Your knee-jerk reaction is to say something about acceleration. And I can say something about acceleration. A sub X equals 0. Is it true? Because what is the minimum F that will just start the sled? And you might say, hey, Chris, it's not 0 because the force has moved the box. You have grown this force so much that the box is moving up the ramp. But we are looking just at that break-even point. We're looking at the boundary between this force being not quite great enough versus great enough to move the box. So we're looking right at that inflection point, right at that threshold, which is why I'm saying A sub X equals 0. Box is at rest at this threshold, at the threshold. Now, if you punch through the threshold, then the box starts to move.
Okay, so just for clarification purposes, so you're operating under the assumption that there is acceleration, just enough just to barely move it, but it's going to be so close to 0 that you're going to assume it's 0, like at that inflection point?
I'm operating on the assumption that this force vector, this force right here, just reaches the value it needs to reach so that it will overcome MGX and FS to start the box moving. So right at that boundary, you could say the acceleration right at that point is infinitesimally small. So infinitesimally small, or you could say it's 0 right up to that point. Probably the right way to say it is, as soon as I hit this magical threshold with this force value, the acceleration at that moment becomes infinitesimally small. It goes from 0 to being basically 0. So that's probably the better way of putting it. So then let's update this. I have minus, I'm going to process number 11, minus F sub S, which is minus mu sub S times F sub N. We've seen that before. Minus MGX, it's the same trig, MG sine theta. We've seen that before. Yes, plus F equals 0. And then I guess we can say, again, there's that f sub n. So once again, find, or f sub n, I should say. F sub n is found in number 11. So we did the work. We already did the work to find f sub n. Okay, so it's the same thing. This is the algebra time. So again, speaking to those of you who still don't cut through algebra like a fish cuts through water, because I do have these two statements. I have, this is my X-force inventory. That's the reason, this is my new X-force inventory. So I'm going to combine this with this, and this remains the same. Nothing changed in the Y dimension. So I'm just going to go ahead and combine, use number 11 again. Yes, 6, 7. This should have been fine down here. Find f from number 6, and I should have read, this should be number 11 and number 11. So just let me fix that. So you're going to use number 13 and number 11 to find f. So let's find out what kind of force is needed to just almost barely get the penguin moving up the ramp. Okay, we can do that right now. And that's the answer to part B. Done with part A, done with part B. But
could you explain what you have highlighted in 13? I don't really understand it.
13?
Yeah.
Start with number 10, Quentin. Read through. Start with number 10, and then read number 11, and then number 12. And then after you review yourself, step 10, 11, 12. Tell me if after reading 10, 11, 12, you're still not understanding where 13 came from. And then we'll chat some more. But just take the moment to do that.
Professor?
Yep.
The problem locked. I can't see it.
Okay, let me fix that. Taking an enormous amount of time on this problem, but I think it's justified. I think this is a lot of fundamental stuff. This is the heavy lifting approach, which pays dividends. Chapter 6, quiz 1. Okay. All right, you should see it now. And again, let me see how people are doing. I don't want to move too fast, but I don't want to move too slow. And again, for those of you who are kind of stuck and maybe not feeling it, I mean, this is a job for tutors and office hours. So when I say you just need to spend more, I mean, that's one thing to say, oh, just spend more time, but spend more time consulting tutors in Schoolcraft's Learning Services Center, Learning Support Center, Learning Support Services. Schoolcraft provides tutors. I provide office hours. So you definitely should start thinking about what do you need to do to help yourself. All right, but a good number of people are done with part A and part B. Let's move on to part C. For those of you who are not done with part A and part B, I'll add some stoppage time at the end of all of this. So again, there's no reason whatsoever why you're not going to get this question correct, because all you have to do is just request some quiz deadline extensions, and the answer is yes, you will always get those. Part C is different. Well, they're all different. B is different from A, and C is different from A and B. What value of F is required to move the sled up the plane at a constant velocity? So you know what? This is new. This is new thinking. In fact, if at this point, you guys, let me make a suggestion. If you're still working on part A or part B, stop, just because then your problems are going to get compounded. Just stop working on part A, stop working on part B, and stay synchronized with me for part C. And then you can go back and finish off, because otherwise you're going to lose. You're just going to fall behind. So part C says, now I have increased the force enough so that I break through static friction. So I'm going to say this: F increases enough to overcome friction, static friction. F increases enough, and I should say this: F increases enough to overcome mgx, which is going down, and static friction. So I have defeated static friction with this force. Once I defeat static friction, box moves, and is now subject to kinetic friction. So this is different, and it makes sense. I've broken the boundary. I've broken the stickiness between the ramp's static friction and the penguin box. And now, so the box is moving up the ramp, and now it's exposed or subjected to kinetic friction, F underscore K. And F underscore K, and you should already have this written down in your green sheets, is mu sub K times F sub N. So notice the similarity between F sub K and F sub N. F sub S. I'm sorry. Notice the similarity between F sub K and F sub S. F sub K is mu sub S times F sub N. And this is F sub K. All right. So let's go through it. So now I got to update nothing changes in the Y dimension. So I'm going to erase my static friction force. And now I got to think. This is the thinking part. This is where you ponder. So there's lots of opportunity for pondering when you do these problems. If I've increased my force enough to overcome mgx, and which is pulling me down, and static friction was preventing motion, the box now starts to move up the ramp. So I'm going to indicate that my box now has a velocity. My velocity is now up the ramp because I've broken through static friction. But this is how I'm going to draw my kinetic friction vector. My kinetic friction vector is again down the ramp, but instead of F subscript S, it's now F subscript K. And one great thing to remember about kinetic friction: F sub K. Kinetic friction always opposes velocity. So if the velocity is going up the ramp, the kinetic friction is going down the ramp. And another good thing to note: F sub S always opposes velocity tendency. So for example, if I was pushing in part B, I was pushing up the ramp, and basically I was just about to start the box moving up the ramp, which means it would start to have a velocity up the ramp. And that's how I figured out, static friction opposes the velocity tendency. The tendency would be to go up the ramp, and static friction opposes that. up to its limit, because static friction can't deal with a force that's just too great. So these are two good statements. Let's do another X force inventory, number 18. All right, so here's my new X force inventory. The Y force inventory is completely unchanged. I just have sum of all the X forces. And then this is where, again, the free body diagram is critical. I've got minus F sub K in the negative X direction, minus MGX, which is also in the negative direction. And that's it for the negative X direction. Then I have F. That is it. So this is getting easier as we go along, because we just have to update the X force inventory. The Y force inventory stays unchanged because nothing is changing other than my static friction vectors. Next step is say something about acceleration. And what you're saying about acceleration, and this should be A sub X, not A sub Y. Ooh, we have to think about this. Because this is not motionless. I was going to write down the penguin is motionless, but the penguin is not motionless. The penguin is moving. So I can say this. I'm going to say acceleration equals dv dt, or macroscopically, you could say delta v over delta t equals 0, because velocity is constant. The problem indicates velocity is constant. So the box is moving, but just because the box is moving doesn't mean it's accelerating. In fact, in this case, it says the box does move, but it's not speeding up or slowing down. So I do know that acceleration equals 0. That's a big deal. Step number 20, here it is. Here's my X force inventory for part C. Minus mu sub K times F sub N minus mg sine theta, looking very familiar, plus F equals 0 again. And we know for the umpteenth time, no, we're good. We're good. I'll say use number 20 and back to number 11. The normal force has never changed because nothing in the Y dimensions have changed. Use number 20 and number 11 to find F. This is the force that's pushing the box up the ramp at a constant rate. If I do this, let's see, I have a new coefficient. The coefficient of kinetic friction is 0.170. So note that for sure is different. Times 70 times. Okay, 34 and some change. Weird. Why is it that I can apply a smaller force to move the penguin up the plane than it took me in part B? In part B, I had to apply a huge force to overcome static friction. But in part C, I can see once I overcome static friction, I can back off. I don't have to apply 41.3 newtons anymore. I can apply 34 to keep it moving. That is, again, once I break through static friction. This is the answer to part C. So we are done with A, B, and C in their entirety. It is now 2:19. So I'll do this. You guys can keep working on this, and I will. Let me check the deadline here. So for those of you who are still catching up, you can catch up. You can easily catch up now. I just want to check the deadline for this assignment. This was chapter 6, quiz 1. All right, good. So it's not due until 3 o'clock, but so that's more than enough time to finish. And then let's now take a 8-minute break, which is 2:28. See you at 2:28 p.m. Feel free to talk amongst yourselves. Again, for those of you who are still maybe need an assist with the algebra, which is totally understandable. Don't get me wrong. I'm just saying it's time to think about using tutors and office hours and pulling out those types of tactics. So see you at 2:28 p.m. A box on a ramp, yet another box on yet another ramp. It's initially at rest. And now, for some reason, they don't really have to, but they're saying the positive direction of the x-axis is up the plane. And I would say, well, I would have figured that out because I know all about how to select coordinate systems. But they are saying they are making this stipulation. And so they're saying the positive x-axis is up the plane, which is fine. You don't need that assistance. You can figure that out by yourself based on the criteria, based on the coordinate system selection criteria. All right. So here's a question. We know all about this system. And now the question is, what is the frictional force on the box from the plane when P equals this value? Okay. So let me just start. I'm going to start with number one. This is a job for force analysis method. Okay. And we have all of the force analysis method recipe items. There's the free body diagram. There's the coordinate systems. It's only one body. There's decomposition. There's the inventories. And then there's the acceleration statement. And then there's crunching. So this really should be familiar to you. All right, so this is a job for FAM, which means, now let's see. I have friction, so I'm not able to ignore friction. And the part A says, what is F sub S? So my dollar sign is, the dollar sign is friction. So now here's the question. Friction is the dollar sign, friction force. Friction force is the dollar sign. So now my question is, when I read that, it says, what is the frictional force acting on the block from the plane? So I'm saying, well, if they're asking me to find out the friction force, are they talking about kinetic friction or are they talking about static friction? And the answer is, I don't know. So I'm going to read through the question again. It says, this force P, which is right here visually, is acting on a box weighing 48 newtons. The block is initially at rest. So that's noteworthy, I suppose. Maybe. It's initially at rest. I know theta. Positive X is up the plane. So I took care of that. And now they are giving me the coefficient of static friction and the coefficient of kinetic friction. And they want to find out this frictional force. So again, I'm going to repeat my question. Does this mean I need to find F sub K or F sub S when P is negative 5.1 newtons I hat? All right, so let's see. Number 3. I have a question. Does, or I'll say is the combination, combo for short, is the combo of P, that P force indicated visually, and mgx enough to overcome static friction? And static friction is written as F underscore S question mark. So I need to do sort of a situational test here. And before I get too far ahead of myself, here's the free body diagram. So let's do the whole free body diagram thing. We're getting really good at this. I have weight going, that's a little bit too thick. I have weight going straight down. acting on the center of mass. There's weight. This is my P force. I'll just redraw it again. This is my P force, my externally applied P force. And at this point, this is weight, mg, W equals mg. This is the P force right here. I'm just going to overdraw that again, reinforce it. Weight is a vector. All right. So I'm not going to draw friction because, to be honest, what kind of friction do I have? And what kind of friction I have is going to be based on the combination of the P force and mgx. And here's mgx. I keep saying mgx, and you should know this by now. You should see that when I break things into components, that's the y component, and this is the x component. So we've seen this a lot. You know that this is mg y, and you know that this is mgx. And let me erase this, maybe just clean this up a tad bit. And the hypotenuse there is mg. So we've seen this a lot of times, and you're just seeing it one more time. But now I have to do like a means test. And I'm going to read this sort of reflective question one more time. Is the combination of P, which is right here, P, and mgx, which is right here, those are both down ramp forces. Are they enough to overcome static friction? So that's my first test. And I'll say, I'm having this dialogue with myself, and I would say, well, what is F subscript S? And then the answer to that is F subscript S. Static friction is this stickiness factor, mu sub S. This is the coefficient of static friction. Once again, a sheet of rubber is much stickier than a sheet of ice. So rubber has a much higher coefficient of static friction. And there's a lot of stuff I'm leaving out that's just quite honestly available to you in the lecture video. So just another plug times F sub N. That's the answer. That's how much static friction I have generally. Specifically, here's how much static friction I have. I have mu sub S times the normal force, which is mg cos theta. We've seen that. And I guess technically speaking, if I wanted to be airtight, I would maybe do a 5a and do a y force inventory, saying that the sum of all y forces is I have the normal force going up and mgy going down equals mass times acceleration. And this would be y. And my acceleration statement is a sub y equals 0, since the box doesn't leave the ramp, since there is no plus or minus y motion. Okay. So then we're saying 5c F sub n equals mgy, which is mg cos theta. So I've done this a lot of times. I was sort of tempted just to skip and say, well, we've done this so many times, but that seems a little bit cavalier. So there's 5a, b, and c, 6, got it. So here's how much static friction we can cough up. Ready, set, go. F sub s equals mu subscript s, which for me is given 0.510. Mu sub s is 0.510. There's no units there. Times mg. I don't know m, but I do know mg. Mg is the weight, and weight is given as 48 newtons. Yes. Cosine of theta is cosine of 18 degrees. So if I need it, my static friction can provide up to 0.51 times 48 times cosine of 18. I can cough up. My static friction can scale up. Static friction will Static friction will increase or decrease to be whatever it needs to be and nothing more. So if needed, I can get 23.28 newtons of static friction. That's good to know. And let me say this again, static, and this is in the lecture video. Static friction can be greater than or equal to 0 or less than or equal to mu sub s f sub n. So it's kind of tricky. Static friction scales, meaning if you don't need it, if it's not needed to keep things motionless, it will be 0. If you need it to grow to a certain point to maintain a static situation, it will grow. It will keep growing until it can't grow anymore. And at that point, you've exceeded its threshold. All right, so then, okay. What is the combination? What is the combination of mgx, which is trying to pull the box down, and what is the combination of mgx and p? And this will tell me, is this box going to move or is it not going to move? So here's the combination: mgx plus p, mgx plus p. And these, again, what I'm drawing here in step 10, these are the downward oriented forces that are trying to drag the box down. Static friction is trying to resist those. Static friction is trying to counteract those. So here's mgx. Mgx is mg sine theta plus p. So let's just keep going with that. This equals mg 48 newtons times sine of 18 degrees plus p, and p for part A is 5.1 newtons. They gave you p in unit vector form, 5.1 newtons. So right here, let's talk about this just for a second. They said this externally applied p force is negative 5.1 newtons in the I hat direction. And that's right here. That's what I'm drawing right here. This for part A, this is p equals negative 5.10 newtons in the I hat direction, or negative x direction. All right, so this is how much downward force is acting on this box. I have 48 times sine of 18 plus 5.1. I have 19.93. So I win. Static friction wins. So, aha, big moment. F sub S wins. Okay, so you know what it means. Because this is a great story to tell. Fascinating too. I can cough up, if needed, I can cough up 23.28 newtons of static friction. But for part A, I only need 19.93 newtons of friction, because once again, this 19.3, this is the down ramp. This is down ramp force. So I just need
You still there?
Professor, you good?
Break time?
No, I think his internet probably crashed. Or something, but
now that we're back. To recap, I have shown that these two forces, mgx is a down ramp force, p is a down ramp force. They combine to exert 19.93 newtons of downward force on the ramp. And the good news is, from a static friction point of view, I can meet that. So number 11. Okay. Success. F sub S in this case equals 19.93 newtons. That's the answer to part A. And again, just so it's not clear, or just so I'm being confusing. No, I mean to say static friction can grow to be as great as 23.28 newtons. It doesn't need to grow to that point. It just needs to grow to 19.93 newtons, because if static friction is 19.93 newtons, everything remains motionless, which is the criteria. All right, let's move on, because now we have a different P force. What happens if you crank up the force? So basically you're saying, I'm getting impatient. I want to move this box down the ramp. So now part B, step 12, part B is saying, what if you increase? What if P, this down ramp force, is now 8.4 newtons down the ramp, like that? Everything stays the same. So we can kind of fast track this now, but not cut corners. Okay. I still, F sub S can, once again, provide up to 23.28 newtons of up the ramp force. That's the max. That is what the static friction force can scale to provide of up ramp force. Okay. What's the down ramp force? What now is the down ramp force? And the answer is still the sum of those two vectors. It's still going to be mgx. Mgx is a downward force. So is P. That's a downward force. And with numbers now, I have mg sine theta plus P, or mg is 48 times sine of theta, and theta is 18 degrees, plus P, but P has grown. P has now grown to be an 8.4 Newton force. So numerically, what I have now is 48 times sine of 18 plus 8.4. Right, so now this is my total downward force, 23.23 newtons. So step 16, I guess I'll go here.
Do you mean to use cosine, or are you supposed to be using sine?
You tell me. What should I be using? If my goal is to capture mgx, what do I do? So what do you do to express mgx using this triangle? Do I use sine or cosine or tangent?
Yeah.
And just to play it out, just because this is good reinforcement, I would say, well, if this is the angle theta, and these two are, and I know this might be a little hard to read, but maybe not. I know this. I know sine of theta equals side opposite, which is mgx, over hypotenuse, which is mg. And that's how I'm saying mgx equals mg sine theta. Okay, so I have this much downward force. So the question is, can the static friction force scale to meet or to offset this 23.23 Newton down ramp force?
Hey, Professor, can you just move your screen down just a little bit?
Yeah. And hopefully this isn't too small to read. Okay.
No, that's perfect. Yeah.
Okay. All right. So there it is. There it is. So 17. Great success. Again, for you Borat fans, great success. F sub S does indeed offset this force, this down ramp force. And I've already shown that. All right, so the answer is F sub S equals 23.23. So again, this is the sort of the trickiness or the challenge with static friction. Static friction is scalable. It grows only to what it needs to be to keep everything motionless until you exceed its limits. And then here's the ultimate example. We go to a toboggan hill on Hines Drive. I'm sitting on a toboggan, and it's snowy, it's snow-covered ground. You push me, and you know from experience, it takes a lot of force to start me moving because you have to overcome all of that static friction. But you know this from experience. Once you get me moving, you can kind of back off. It takes a lot less force to keep me moving at a constant speed than it does to get me to move to begin with. And that's exactly what's going on here. Static friction will keep me motionless until you basically punch through. And then once you punch through static friction, then you're encountering kinetic friction. So this is the answer to part B. Done with part B. Yes. Where did I say done with part A? Well, we're done with part B. Okay, this was part A. All right. Let's do part C. Same thing again. Everything's the same, except you are getting increasingly impatient. Step 18 says for part C, now this P force that you're applying equals negative 15.4 newtons. So it's going to be the same chain reaction of Q and A. How much downward force do we have? Here's the amount of downward force. So maybe I'll just say F down. The total down ramp force equals mgx plus P for the umpteenth time. And we know mgx is mg sine theta plus P. So with numbers, here's the downward force, F down equals mg, which is 48 newtons times sine of 18 degrees plus P, and P has now grown to 15.4 newtons. So here's the total amount of downward force. 48 times sine of 18 plus 15.4, 30.23. So that's it. Finally, we have defeated static friction, 30.23 newtons. That is the total downward force. So F sub S is finally defeated. So that means the box moves. Box moves down the ramp. So if the box is moving down the ramp, the friction it encounters now is kinetic friction. The friction exerted on the box as it's now moving down the ramp is kinetic friction, is F sub K, not F sub S. All right, so because this question is saying what's F sub K, because the question says what's the friction force? What's the friction force in this situation, in the part C situation? The friction force is F sub K, because again, the box is moving. There's no more static friction. There's kinetic friction. F sub K equals the stickiness factor, mu, like mu2, subscript K for kinetic, coefficient of kinetic friction times F sub N. And we know that F sub N is mg cos theta. That's the answer. And again, just over here, just one more triangle game. If cosine of theta equals side adjacent is mgy over hypotenuse. This is how I'm getting mg cos theta for f sub n. Okay, so now just plug in numbers and you'll be done with part C, 23. I've got mu sub k, which is 0.34. There's no units, times mg, which is 48 newtons, times cosine of 18 degrees. And this is the friction force, which happens to be kinetic friction. 0.34 times 48 times cosine of 18, 15 and some change, 15.52. Okay, newtons. That's the answer to part C. So these problems, these are good. I mean, don't be misled, you guys. I am taking far more time than it would take you to do this, but that's just because I'm taking this opportunity to really drill down into some basics, some commentary. All right, good problem. I need to get quiz 3 ready. Let me come back to this page in a second. Quiz 3 is problem 18. You guys can do that as I get quiz 3 ready. Time check 3:02. All right.
Okay, I just have a quick question about part B.
Part B.
For my part A, or no. For my static friction, I get 22.3117.
Okay.
And then for my part B, I'm getting 22.314. So that's greater than my static friction.
Maybe that's true. I mean, I'm not.
So, but should I still be getting the wrong answer?
No, I don't think there's a. No, you should not be getting a wrong answer. So
Okay.
let's circle back to that. Just again, I'll add stoppage time at the end, and we can revisit that issue.
Okay.
And I can do that for anyone else who needs to go back and troubleshoot. But for now, you should see chapter 6, quiz 3. And if I played my cards right, chapter 6, quiz 3 should look like this. Oh, this is kinematics, and so a special. You get a bonus. This is kinematics and force analysis. So this is KAM and FAM, which is good. Those are special. Anytime you can combine topics like that. Okay, let's do the read through. And this is 618. You testify as an expert witness because once you've taken Physics 211, you qualify to be an expert witness at many trials. And your job is to find the impact speed. So let me read through this. You testify as an expert witness involving an accident in which car A, which for me looks blue. So car A is this blue car. This blue car is cruising down a road. Let me just read through. This blue car slides into car B, because why? Car B, which is this green car, is sitting here stopped at a red light. So this is sitting here perfectly motionless. You're driving this blue car, car A, automobile A, object A, and then all of a sudden you see that the green car is sitting there stopped. At this distance, oh wait, you slam on the brakes. So you slam on the brakes when the driver of car A puts the car into a slide, meaning you slam on the brakes because it lacked automatic anti-brake lock system. I think that should be anti-lock brake. But anyway, imagine the terror. You're driving down this ramp. All of a sudden, you see this green car stop there. You slam on the brakes and you crash into the green car. And the question that we have to figure out, what is the impact speed? What is the impact speed between the green car and the blue car? And I'm saying that because this is green and this is blue. What is the impact speed? And then we need that for this case. It's probably an insurance company case. All right. So to me, right away, I'm just thinking kinematics. Number one, this is a job for kinematics. This is a job for kinematics analysis method, KAM. Okay. So you know what that means. There's a whole recipe. Do the recipe, apply the recipe. Just like the force, apply KAM recipe. The KAM recipe means let's label everything. Okay, and you know what else I'm going to do here? I'm going to for the coordinate system, I'm going to play the same coordinate system that I always play. What should I do with my coordinate system? I know this blue car is going to accelerate along the ramp surface. So here's a question. Does this blue car accelerate down the ramp? Is this the direction of acceleration? So again, it's after I slam on the brakes. When I slam on the brakes, does the blue car continue to accelerate down the ramp, or does it accelerate up the ramp? And the answer is, I don't know. So because I don't know, I do know one thing. The acceleration is for sure along the ramp. So because I don't know, I'm just taking a wild guess, and I'm going to call this plus X. For no reason, the one thing I do know, let me just repeat that, is I do know whatever the direction of acceleration is, it is along that. It is in that direction. Maybe it's in the opposite direction, and I'll find out soon enough, I guess. All right, so that is my x-axis. This would be my y-axis, kind of overlapping things. Okay, so I'm good to go as far as that coordinate system is concerned. Now, again, I'm doing the CAM recipe, which will be stipulated on the exam one. Exam one will say, hey, solve this problem and make sure you specify every aspect of the CAM recipe. And you have that in your green sheet, so you're good to go there. All right, so what do I need to specify? I need to specify all the kinematics things, and you've seen this before. I'm going to call this X initial. This is going to be X final. That's the point of impact. X initial, I guess I'll just call 0. That's fine. VX initial. So you slam on the brakes. When you slam on the brakes, your car, in my case, my car is going 16 meters per second. 16 meters per second down the ramp. And down the ramp is called plus. So this is for sure a plus. That's good to know. A sub x. A sub x equals, I have no idea. The only thing I know about A sub x is it's going either down the ramp or up the ramp. What else can I say here? Vx final. Vx final right here. Vx final is the dollar sign. So this is my dollar sign, Vx final. Vx final. That's the dollar sign, the impact with which the blue car strikes the green car. Time is, I don't know, and I might not care. That's it. I've got my coordinate system. I've got my label, all of my kinematics labels up and running. And now the next question is, what do you guys think? Is this, let me move over here in case I'm getting too low on the horizon. Number 4. Here's the next recipe item. Is this constant acceleration kinematics or is this variable acceleration kinematics? If it's variable acceleration kinematics, this is a job for calculus. If it's constant acceleration kinematics, it's a job for the big 5. And you know what? I'm thinking this is constant. This is constant acceleration kinematics because every force acting on the blue car is constant, which sort of begs the questions. What are the forces acting on the blue car? So I'm going to do that here. I'm just going to I'm going to sloppily overlay things because I don't think it's that hard to see. Okay, so ready? Force analysis. So I'm kind of bleeding over into force analysis method. This is the normal force. This is the weight force. And this is the friction force. Because I'm skidding. I'm skidding, so I know for sure I have friction. I got to label this stuff. Not only I'm skidding, I know I have friction, and I know it's kinetic friction. So there's no uncertainty there. The blue car is skidding down the ramp. Kinetic friction always opposes velocity. If the velocity is down the ramp, kinetic friction is up the ramp. This is my normal force, F sub n. This is my weight force, mg. Okay. I guess I have to decompose because I have one two-dimensional vector. So this is business as usual. This is really probably starting to look pretty familiar to you by now. We've done this so many times. This is mgx. This is mgy. Okay. And this ramp angle theta there is this ramp angle theta here. So I know I'm being I don't know if overlapping all this is such a good idea, but it seems convenient. Hopefully you can read it. All of these forces that you see in this free body diagram, they're all constant. None of them are varying as a function of time or position. So this is constant acceleration kinematics, which means you now use a 6-column data table. Just like always. All right, so X initial, X final, Vx initial, Vx final, A sub X, and T. And now it's just a game. What do I know as far as these entries are concerned? X initial is 0. X final is D. So for me, this is 23 meters. This is given. D equals 23 meters for me. My initial X velocity is down the ramp, so that is a positive number. And as mentioned, it is 16 meters per second. This is my impact velocity, VXF. This is I don't know, and I don't know. So for number 8, I'm going to write, too many unknowns. Too many unknowns. But you're not going to panic. And how do I know there are too many unknowns? Because if I just say, well, I don't know time, I don't know acceleration, I don't know final velocity. That's too many unknowns. So now what is the question? Number 9, now what? And a knee-jerk reaction is, for me at least, look at a Y-force inventory. or no, not look at Y data. But I don't think that's going to help me. I don't think looking at the Y data is going to help me as far as finding out any one of these variables. It's just because this is Y, the Y data. There's nothing happening in that dimension that I can see any connection with the final x velocity, a sub x or t. Okay, so unlike projectile, this is not 2D projectile motion. In that case, you could find something from the Y data. So I'm going to look at Y data. No. Look at force analysis. Look at FAM. All right, so if I look at FAM, and I know FAM is all about just cranking out F equal MA equations over and over again. And there's A. So, I mean, acceleration is sitting right there in Newton's second law. So that's the path I'm going to go down. All right, so I'm going to say my X force inventory looks like this. Sum of all those X forces acting on the blue car. And this is where your free body diagram needs to be very accurate and complete. I've got MGX pulling the car down the ramp. Yes, I do. Is that it? I suppose. And then I got kinetic friction trying to stop that downward motion equals MAX. The next thing you have to do is say something about acceleration. And there is something to say about acceleration. A sub X, in this case, is the dollar sign. So that's good news because if I process this, if I process my X force inventory, I've got MGX, which is mg sine theta, yes, minus FK, which is mu sub K F sub N, equals MAX. What's F sub N? So this really does look pretty familiar. You hopefully are starting to see like repetition. What's F sub N? Well, if I do sum of all Y forces, I have F sub N going up, and then down I have MGY equals MAY. Say something about acceleration. A sub Y equals 0 since there is no plus or minus Y motion. In other words, the blue car stays on the ramp. Okay, so for the umpteenth time, you're saying, yes, I get it. F sub N equals mg cos theta. Okay, so that should really be pretty straightforward at this point. All right, so now let's update number 13. Update number 13. This is what I have now. Here's my new and improved number 13. Mg sine theta minus mu sub k mg cos theta equals MAX. And there's my answer to acceleration. My acceleration is A sub X equals mg sine theta minus mu sub k mg cos theta all over m. And you can see some cancellation. So this gets simplified. M cancels, M cancels, M cancels. I'm going to get a number on that, and I'm going to keep this number and store in calculator memory location A. All right, so let's get a number on that, and then it's back to kinematics. G, 9.8 times sine of 14 minus mu sub k, which is 0.58. It's a dry road, times 9.8 times cosine of 14. I get this. Ooh, I get a negative number. That's very interesting. This equals negative 3.144 meters per second squared. And that's sitting here again in memory location A, store alpha A. And let me just redo that a second time just to double check. 9.8 times sine of 14 minus mu sub k, which is 0.58 times 9.8 times cosine of 14 degrees. All right, I'm getting the same answer twice. So note, that negative sign is pretty interesting. Number 19, aha. Blue car, mass A, blue car, blue automobile. The blue automobile accelerates up the ramp. Blue automobile accelerates up the ramp. So the blue automobile is moving down the ramp, but it's accelerating up the ramp. Isn't that interesting? Let me say that again. Yes, for sure. You slam on the brakes and you are moving down the ramp. But as you move down the ramp, as you're moving down the ramp here, you're slowing down. And so if this is your velocity vector, your acceleration vector is up the ramp. And that means slowing down. You're moving down the ramp, but you're slowing down as you move down the ramp. Number 20, let me go over here. Back to kinematics. Okay, so back to number 7, update number 7. Here's the new number 7. Number 7 was my table. So this now, instead of question mark, this is calculator memory location A. I have that. I figured out that number thanks to force analysis. So I'm going to play the Big 5 game. If I now play the Big 5 game, and the Big 5 game says, which Big 5 equation contains the variable you care about, contains the $ variable with all other variables known. And in this case, I'm going to guess this. VXF squared equals VXI squared plus 2A sub X, X final minus X initial. Okay. So before I keep going here, VXF, well, this is the $, so it's okay that that's unknown. Do I know VX initial? Yes, I do. It's sitting there in my data table. Do I know acceleration? Yes, and don't forget the negative sign. Do I know X final? Yes, it's in my data table. I know everything here. So go ahead and solve for the impact velocity. 22. But they don't want velocity, they want speed. So remember, speed, we know the velocity is down the ramp, but they don't care about direction. So just speed equals the absolute value of velocity. And if I do this, let's see, let's get an answer. 16 squared plus 2 times alpha A times 23 square root. Okay, 10.55. This is my speed, 10.55 meters per second. That is the answer to part A, thanks in large part to kinematics analysis method and force analysis method. Now, what I'm going to do, let's see, let me do a time check here. It's now 3:24. Here's what you guys can do for part B. Part B is identical. Part B is identical to part A, except there's wet leaves on the pavement. So things are slipperier. So for part B, everything's the same, except instead of the coefficient of kinetic friction equaling, in my case, 0.5, mu sub k now equals something less, for me, 0.17, because it's slipperier. Wet leaves are slippery. So now much more dangerous, much more sliding. Leaves are slippery. So go ahead, repeat everything. Let me scroll down a little. Well, let me zoom out. you can repeat all of this, and it's going to go quickly. You can repeat all of this for this new coefficient of kinetic friction. And I'll just write that down, number 24. Repeat steps. Everything's the same. I'm just going to say repeat with mu sub k equals 0.17. Okay. And then you're going to get the right answer. And it's now 3:25. So I will say see you at 3:25. Is it? 9 minutes, 34, 3:34. I'll see you at 3:34 p.m. to continue. And all of this is going to help you with chapter 5. This makes chapter 5 look a lot easier. I remember we worked on a problem pretty similar to this in chapter 5. So now what could be different here in chapter 6? My guess is there is friction, so that's probably the difference. All right. Cheerios and Wheaties. The problem statement says, in this figure here, in this here figure, a box of Cheerios and a box of Wheaties are accelerated across a horizontal surface by a horizontal force. Okay, applied to the Cheerios box. And then we do have friction. We have friction on the Cheerios, and we have friction acting on the Wheaties. Okay. If F is 12.5 newtons, what's the magnitude of the force on the Wheaties box from the Cheerios box? So let me state this right now. Let's always use, I think I've said this before, but let's always use the F on what from what convention. The F on what from what convention. On what from what. So what they're asking for here, they're saying, what is the magnitude on the Wheaties box from the Cheerios box? So they're actually saying, what is the force, the magnitude of the force on the Wheaties? So W comes first from the Cheerios. C comes second. So I would read this right here. What is the force acting on the Wheaties from the Cheerios? That's because, again, of this F on what from what convention. All right. So let's do free body diagram. Let's do the whole force analysis. So let me get a different. No, that's fine. Here's my free body diagram. It all starts with the free body diagram. There's my floor. Here's my Cheerios box right here. Let me get a different color. Cheerios box. That's my Cheerios box. So let's talk about the forces acting on the Cheerios box. I have the weight force acting down. So this is going straight down from the center of mass. And we can label that mass of the Cheerios box times G. What else? Oh, I have that externally applied force, that F force. So I will add that. This is my externally applied force, F. So this is F. What else? Or is that it? Well, no, there's the normal force. And the normal force technically acts on the shared contact surface. Here's the shared contact surface between the Cheerios and the floor. So my normal force is going to be perpendicular to that. So I'll draw that like this. Okay. What else is that? No, that's not it. Because I actually have a reaction force. I have a force that looks like this. Ready, set. I guess like Ready? Here. What is this force? This is the force acting on the Cheerios from the Wheaties. All right, so this is kind of maybe new. This is a Newton's third law reaction. Remember what Newton's third law says. Newton's third law, N3L. Newton's third law basically says this: forces always occur in equal and opposite pairs. Forces, you'll never be able to find an exception to that. It's kind of fun to think about it. Forces always occur in equal and opposite pairs, which makes life easier. I mean, that's great insight to have as a scientist or an engineer or a technologist. It's great to know how the universe works. I mean, how many jobs out there are disconnected from the universe? My wife works for Ford Credit, and she works on credit card applications. And that's completely devoid of any sense of reality in terms of physical reality. All right, so there you have it. That's the free body diagram for my Cheerios. I'll label that right here. This is the mass of my Cheerios box. I'm going to do the same thing now for my Wheaties. And I think I'll move this over here. I'll use the same. All right, so here's the Wheaties. Wheaties is green, so I'll just draw it like this. I'm not going to draw them side by side. I'm going to draw them offset of it just so we can see things maybe a little bit clearer. Okay, so there's my Wheaties force. My Wheaties object. Okay, just doing some housekeeping here. What's my free body diagram? So I'm going to do the weight force acting on the Wheaties center of mass. This is mass of the Wheaties times G. I have another normal force, so I better worry about subscripts since I have two of them. This is the normal force acting on the Wheaties. So I better call this F subscript N Wheaties, and this is F subscript N C for Cheerios. Okay, and this is mass of the Wheaties. What else do I have? Oh, and you know what? I actually forgot a force for the Cheerios. I forgot friction force. So let me add that right now. Here's the friction force. Ready, set, go. I know it's going in that direction. So this is the friction force acting on the Cheerios. Because the boxes are moving. How do I know they're moving? Because the problem says they are accelerated across the horizontal surface. So I know for a fact that the boxes are moving. If they are moving, there is for sure a kinetic friction force, because kinetic friction will always try to fight velocity. So this is FKW. And I'm going to indicate, because what I just said is worth pointing out. The velocity of the Cheerios is in that direction. The velocity of the Wheaties is also in this direction. Again, I'm showing them separated, even though in reality, this is what's really happening. In reality, the two boxes are side by side. What else for the Wheaties? Oh, here's something interesting. I actually have my Newton's third law, opposite and equal reaction pair right here. I got to move this, I guess. Let me just shrink. One more force acting on the Wheaties. And it's technically a normal force. And it's basically the force exerted on the Wheaties by the Cheerios. And I'm going to draw that. And when I draw it, it looks like this. Ready, set, go. and label it. So this is the force on what? It's F on what? On the Wheaties from what? From the Cheerios. That's my dollar sign. So finally, at long last, I see my dollar sign. There it is. And then a very important note. I guess I'll get started here. Step number one. I'll go over here. Step number one. Aha. Newton's third law says all forces occur in opposite and equal pairs, as opposite and equal pairs. Newton's third law says that whatever FCW is, that's going to be the same as FWC. So that's good to know, especially since this is my dollar sign. I need to find the force acting on the Wheaties from the Cheerios. So off and running, my free body diagram is done. FBD is done. I don't need to do anything fancy with the coordinate system other than address it. Here's my coordinate system, just standard coordinate system. I don't need to rotate, so I'll just draw it right here. For both objects, this is going to be plus X, and this is going to be plus Y for both objects. Okay, done with the coordinate system. I don't need to decompose because I don't have any two-dimensional vectors. And now it's time for the X force inventory and or the Y force inventory. Here goes, number 2. I guess I'm going to start on the Wheaties. Look at the Wheaties box because that's where my dollar sign lives. So if I look at the Wheaties, this is what I have. I have plus FWC, that's going rightward, right there you can see, minus FKW, minus the kinetic friction force acting on the Wheaties. And I guess that's it, isn't it? Okay, and it equals mass of the Wheaties times A sub X. Because I should have started off a little bit sloppy here. I should have started this off with great care that says the sum of all X dimension forces. Okay. So let's say something about acceleration. We need to make an acceleration statement. And here's what I'm going to say. I'm going to say whatever the acceleration is on the Cheerios, A subscript C, that's going to be the same as the acceleration acting on the Wheaties. And so let's just call that A. And because mass of the Wheaties, or the Cheerios box and Wheaties box move together because they're just right next to each other. And if you push on them, they're going to remain right next to each other. So that's an important statement. All right. Let's number 4 then. What do I do? Isolate FWC because that is my dollar sign. FWC, the force on the Wheaties from the Cheerios, is the dollar sign. So I have FWC equals mass of the Wheaties, acceleration X plus FKW. And let's see, what do I know? Am I done? Could I possibly be done? I know FKW. That is the kinetic friction force acting on the Wheaties. And that for me, what is the magnitude? For me, the magnitude of the frictional force acting on the Wheaties is 4.6. So I know this number. This equals 4.6 newtons. So I know that. Do I know mass of the Wheaties? I do. Mass of the Wheaties is 2.9 equals 2.9 kg. Okay, the only problem is I don't know acceleration. So trouble in paradise, but not to worry. Now what? Number 5, how do I find X? How can I find A sub x, I should say. How can I find A sub x? And you might be thinking, well, do a Y force inventory. Maybe, but I can't see. Well, maybe I will have to do the Y force inventory, but I remember this is the tactic we used in chapter 5. We basically treated both of these boxes as a single object. So I'll just draw one box. This one box here can be considered to be a single object. So I know the mass of this box. The mass of this box is the mass of the Cheerios plus the mass of the Wheaties. Yes, I know that. What are the forces acting on it? I have the weight force acting down. So this would be mass of the Cheerios plus mass of the Wheaties times G, because weight is mg. I know the normal force is going up like that. So this is the normal force, F sub n. I have this externally applied force on the Cheerios, and I think, oh, and then I have my two friction forces. I have the friction force acting on the Cheerios, FKC, and then I also have the friction force acting on the Wheaties. So those two friction forces, they're still there, FK Wheaties. So now that I'm considering this as a single system, these two boxes are staying together. So I'm just going to consider them to be a single object. Let's do an X-force inventory. Let's do an X-force inventory on MC plus MW, the two boxes together. When I do that, I get sum of all the X dimension forces. And again, I remember this tactic from chapter 5. So that's where it came from. All right, so I have minus FKC, the kinetic friction of the Cheerios. Yes. Minus FKW, the kinetic friction force acting on the Wheaties. And I guess that's it. Plus F equals mass times acceleration. Say something about acceleration. And I can say something about acceleration. I can repeat myself because I said previously the acceleration of the Cheerios is the same as the acceleration of the Wheaties, and let's just call that A. So maybe I better say, in this case, let me fix this. Here's my acceleration, A sub x. In this case, equals A sub c equals A sub w. So that's a little bit better. And right now I can find this, I think. Solve for A. So from step 7, here's what I get for A. A equals minus FKC. And I know numerically what that is. Minus FKW. I know that numerical value plus F. I know that numerical value divided by M. And I might need to update this. This is the mass of the Cheerios plus mass of the Wheaties. And let me just go back and repair this a little bit to be a little more tight. F equals MA. And more specifically, the mass is mass of the Cheerios plus mass of the Wheaties times A sub x. Okay, so hopefully you can see clearly how number 7 comes, how number 9 comes from number 7. I guess this is all good. Okay, so you're going to get a value for acceleration, and then now solve number 4 and be done with it. Now that I have acceleration, and I have numbers on everything in step 9. Mm-hmm. Turn on the calculator. Okay, and that's my answer. Time check. It's no. Let me set up one more quiz. You guys can keep working on this for a bit because I'll need a bit of time to get things set up. Quiz 5 is, wait a minute, 1, 2, 3, 4, problem 29. Okay. Let me check status. That was chapter 5, quiz 4, chapter 6, quiz 4. Everyone's done. All right, last quiz, I think, isn't it? Yeah, this will be the last quiz. Chapter 6, quiz 5, I think is looking like this. One more. Let me say again that this is definitely going to help you, I think, prep for any chapter 5 problem, which will be obviously as part of exam 1. And just to reinforce, because I should have been making this point sooner than today. But going forward, I need to make sure you guys realize that you do have Schoolcraft Learning Services. You guys really do have a great resource right here that I'm showing, learning support services for all kinds of tutoring. And this would be the resource you use if you have, I mean, you can have physics questions, obviously, but really, I think the most immediate benefit would be they can help you with trig, algebra, and calc, all the prerequisite stuff. And on top of that, physics, obviously. So just wanted to remind you guys about that. All right, so now we have another block and pulley. So it's one of these kinds of problems. So we're starting to see, hopefully you're starting to see that there's a certain amount of variety in force analysis, but there's not an infinite amount of variety, which is good. You have to get your arms around the variety that we have here, which is not unreasonable. This is not a crazy heavy workload. All right, so this says this says in the figure, blocks A and B have, so I know the weight of block A, I know the weight of block B. Fine. Determine the mass of block C that's needed to keep things stationary. Determine the minimum weight of block C to keep A from sliding. That's the question. That is the question for part A. So free body diagram time. Recipe item number 1. And now I have 2 bodies. So I'm going to have 2 free body diagrams. All right, so it looks like this. And you know what I'm going to do? I'm going to combine mass A and mass B. I'm not saying you have to do it. I'm just saying I'm just going to do it now because they're sitting right here. They're moving together. So, okay, I'm just going to call them a single mass. So I'm going to call them a single mass, and I'll just call it mass of AC. Mass AC is the combined mass of block A and block C. Okay, so what are the forces acting on that? Let's do the free body diagram. I have tension pulling to the right. I have the normal force, or the weight force, I should say, is going straight down. I have the normal force, which initiates at the shared contact surface. There's my normal force. Do I have friction? I do have friction. And remember what static friction is telling or is doing. Static friction, F subscript S stands for static friction, opposes velocity tendency. It doesn't oppose velocity. It opposes velocity tendency. So you can see in this situation, what's the velocity tendency for block AC? Well, you can see this is the tendency. This is the velocity tendency. If it was going to move, it would move to the right. Now, it's not moving because of static friction, but that's why I'm calling this is the velocity tendency. And the only reason I'm doing that is to make sure I know to draw the static friction force like this. It's the static friction force that's keeping things motionless. All right, so this is static friction force. This is MAC times G, the weight of block AC. Up here, this is my normal force. Got it. This is my tension force acting on AC. I'm done. I'm done with the free body diagram for block A. What about for block AC? What about for this mass right here? I've got tension going up. This is tension acting on B. I've got the weight force pulling block B downward, acting from the center of mass. Okay. This is mass of B times G, and that's it. Those are my only 2 forces acting on block B. And I can say this right here. I can say the tension AC, that tension AC force is in fact the same as the tension acting on B. So let's just call it T. Why is that? Same string. And technically I should say same string massless pulley. Because in a subsequent chapter, we're not going to say the pulley is massless. And if the pulley is not massless, it does change things. So for now, that's a valid statement. Okay, we need to find the minimum weight of block C to keep things motionless. The minimum weight, not the minimum mass, the minimum weight. So I'm going to let's start with an X-force inventory. So here it goes. the sum of all x dimension forces, and I should say for MAC. Okay. So if I add up all of those x dimension forces, I've got minus Fs, because that's going in the negative x direction, plus T. That tension is going towards the right. I guess that's it. Those are the only two forces equals MA. And here's MA. The mass is MA plus MC times acceleration. And I can see, you know what I have to do right now? I actually have to worry about the coordinate system. So back to my recipe. I have the free body diagram, which is done. I have the coordinate system. And now this is, do I know the direction of acceleration? Yes, for sure I do. I know that it's along the table surface. So for block, need a different color, for block AC, the acceleration is along the table surface. So that's good to know. For block B, I know for sure it's vertically up or vertically down. So if I'm calling this plus X, if I'm calling this plus X for MAC, I have to call this plus Y because I need flow. So I need flow between these coordinate systems. So X needs to keep flowing all the way to Y. So that's the flow I'm talking about. Let me draw that again. This needs to flow all the way through. It's hard, easier said than done. This needs to flow all the way through my Y coordinate. So this is what I mean by flow. Flow. That's a flowing. That is flowing. This is flowing. Flow has to be aligned. All right, that's good. That's my free body diagram. That's my coordinate system. I don't have any two-dimensional vectors. So decomposition doesn't need to be done here. There is nothing to decompose. And then it's the inventories. And then the acceleration statement. So here goes. I do have the inventory for block AC. Let's do the inventory now for block B. So I'm going to do a Y force inventory for block B. Very exciting. I have the sum of all Y forces acting on block B. And if I look at block B, I've got negative T because that tension is going upward. And upward is now called negative plus the weight force, MBG, equals M B times AY. Say something about acceleration, A sub Y. I'll say it like this. A sub Y is the acceleration of block B. The block B acceleration is the same as block AC, which means, I kind of forgot this here. I got to go back here and do 2A. Say something about acceleration, which I neglected to do until now. It's not too late, but this should be X. In here, A sub X, this is referring to the acceleration of block AC. And once I'm just gonna repeat this. The acceleration of block AC is the same as the acceleration of block B. So let's just call them all A. Got it. And I'll do that here. Same acceleration statement. And why is this? It's important to note that this is because my coordinate, where am I? I'm in the wrong chapter. There. Why is that acceleration statement true? It's brought to you by aligned, meaning flowing together, coordinate systems. And and same string. There's a string attaching those. Okay. So let's finish this. Step 6. I'm back to step 6. Okay, step 6. Well, here's my Y inventory. I got minus T plus MBG equals MBA. So this is all I can do. I have taken my Y force inventory for block B as far as I can go. And you know what? As I look at block AC, I haven't taken that as far as it can go. I need to go back, and I'm just gonna, I guess, do 2B. I have to return to my X force because I kind of left it incomplete. All right, so if I keep going here, negative F sub S. Negative F sub S is negative mu sub S times F sub N plus T equals mass A plus mass C. So I should have done this before, but I'm doing it now times A. And now 2C is do a Y force inventory. Do a Y force inventory to find F sub N. And you know what F sub N is equal, but we're going to go through the steps anyway, because sometimes it won't be so easy to identify. The sum of all those Y forces acting on MAC, well, I've got F sub N going up, and I've got weight going down, MA plus MC times G equals A sub Y was MA sub Y, mass times A sub Y, and we know that's equal to 0. A sub Y equals 0 since there's no plus or minus Y motion. Block AC just stays on the tabletop. All right, so that's where I'm getting the normal force is in fact the weight of A plus C. Okay, so now that's it. I have, this is my X force inventory for block AC. Fine, there it is. This is the Y force inventory for blocks A and C. And once again, this was the Y force inventory for block B. So from these equations, can you get the weight of C? So here's the thing. Let's get mass of the C. So number, I'm at number 7.
Quick
number
question,
7.
real quick.
Yeah.
Why is FN positive in the Y force inventory? Why wouldn't it be negative?
Right here, you mean?
Yeah, so yeah, why wouldn't that be negative? The one right above it, because the Y is going down. So
This is
wouldn't
for
MA
this is the X force inventory for AC. There's no normal force for block B because block B is not in contact with another object. So this is the X force inventory for AC. Let me just trace through this. I've got friction going to the left, tension going to the right. That's it for the two forces. Mass times acceleration. There's my acceleration statement. So then I end up with, and then here's my replacement for static friction. Static friction is defined as F sub S equals mu sub S times F sub N plus T. All right, so I think step 2B looks good. And then Ty, for 2C, I am doing a Y force inventory still for MAC, not for mass of B. So for MAC, I've got the normal force going up, yes, and I've got the weight going down.
But on the flow diagram, the coordinates, you have y plus y going down. Is it?
I have plus y going down for mass B, but again,
okay.
Step one through 2D is all for mass AC. So does that make sense?
Yeah. So AC has a different plus y going up. Plus y is going up for AC.
Oh, that's a good point. That's a good point. That's a good. So you're right. I have to specify. It's a very good point, really. Let me zoom out. Let me bring things down a tad. Oops, sorry. Okay, you are correct. I specified an X coordinate for AC. I also now need to specify a Y coordinate there. Okay, plus Y. That's a good point you bring up. Okay, so yeah, this Y coordinate here and this X coordinate here, these pertain to MAC. So all of this is the world of mass AC. This coordinate system here, this just pertains to the world of mass B. And what links them together is, once again, the fact that they flow. This axis flows with this axis right here, flow. So that's a very good point. Because you were thinking, I think you were saying, wait a minute, you said the y-axis was downward. I said the y-axis was downward for mass B, but I'm saying the y-axis is upward for mass AC. Although, to be honest, I could have flipped this. If I wanted to, I could have done this and it wouldn't have changed anything. I could have done that and nothing would have changed, but good to know. Good to know you're paying attention to those details. That's definitely a healthy sign. Okay, so does that answer your question, Ty?
Yes, thank you.
Yeah, good question. So now let's combine 2B, 6, and 2B, 2D, and 6 to find MC. I'll stick with this instead of just saying, go knock yourself out with the algebra. Normally, I'm fine saying that, but here, let me just stick with this. I'm just going to line them all up. Here's 2B, negative mu sub S, F sub N. And I'm going to do the substitution right now. So instead of writing down F sub N, here's F sub N. So negative mu sub S times F sub N, there's MA plus MC times G. So good. I have just taken care of this. There's negative mu S Fn. This is negative mu S, and this indeed is Fn right here. Plus T. Let's keep going with number 2B. Plus T equals MA plus MC times A. Okay. Now I'm combining it with number 6. This is what I got from number 6. I've got minus T plus MBG equals MBA. All right. So that's it. I am now going to take these two equations, solve for A. Let's do that. Let's get a numerical value for acceleration, because you can see, for me, the way I do it, you don't have to do it this way, but the way I do it, I'm just going to do equation addition. All right, so this minus T and this plus T will offset each other, which means I'll let you solve for A. So let's all solve for A. And I don't want to steal your thunder because, again, I'm definitely sensing the need for algebra activity. So I'll do mine off screen here. Okay, minus mu sub s. Okay. MB. Acceleration. Minus mu s 0.21. Oh,
Wait, how are we supposed to find acceleration if we don't know MC?
you do know MC. Well, no, you're yeah, actually, hang on. We don't know MC. Oh,
Because
hang on.
I think we're supposed to have A equals to 0.
So
since
yeah,
it's
A
supposed
is
to be
equal
hitting-
to 0. Determine the minimum weight of block C to keep A. So let me update this, and then there's another update here. So let's see, 2B. All right, so let me do some updates here. The acceleration is equal to 0 in this case. C needs to be whatever it needs to be to keep things motionless. So here's some updating. That's fine. All right, so this will be the new 2B. I'll say 2B new. The new 2B is minus coefficient of static friction. So it does get a lot easier, times F sub n plus T equals 0 because nothing's accelerating. And then we can say this. We can say the new 2D new. So this is what we get. We get tension equals mu sub s times F sub n. So let me draw a circle around that. And then over here, this is equal to 0. So, and I should say equals 0. And I should say here equals 0. So number 6, this is what number 6 becomes. I have negative T plus MBG equals 0. So I'll draw a circle around that. This is still good right here. All right, so let me do a little bit of damage control by erasing this. Okay, so I have step 7. Here's my new step 7. Combine number 2D, the new 2D, the old 2D. This is a little bit less than elegant. And 6 new. All right. So I'm going to combine these equations. I'm going to combine this. I'm going to combine this. And I'm going to combine this to get MC somehow. I don't need to solve for acceleration because I know acceleration is there. So you're right, Lewis, you are right. So I have, if I have T equals mu sub S F sub N, and I have minus T plus MBG equals 0, That's right, isn't it? I think so. And then if I have F sub n equals MA plus MC times G, now I think, unless I'm still making a mistake, which is possible, but now solve for MC. And then once you solve for MC, you're going to do step number 9, convert MC to weight, because they're looking for a weight, which means you're going to take weight equals MC times G. So let's get an answer for the mass of C. I want to look at the time. And then multiply by 9.8. So let's go ahead and solve for MC. And I think that's kind of doable. I have Mm-hmm. Okay. Let's see for me. Let's see. Oh, one thing I'll note. What's the mass of B? The mass of B equals the weight of B over G. So for me, the mass of B equals the weight of B, 22 newtons, divided by 9.8 meters per second squared. So this is mass B. Same thing for mass A. Mass A equals weight of object A over G, which means for me, the weight of object A is 47 newtons all over 9.8 meters per second squared. So that is the result for mass A. This is my result for mass A and mass B, which I will need. Oop. This is mass B. This is mass A. Okay. Turns out to be pretty cut and dry. Mass of B. Minus mass of B. Minus MA. All right. Mass of C for me is 57.8 newtons. That's the answer to part A. What's part B? What's the acceleration of block A? Huh. All right, so we're running a little bit overtime here. So what I'll do, I'll keep going here. I think all these quizzes are open till 5. So I'm just going to keep going, knowing that you might have other commitments you need to get to. But for part B, what's the acceleration of block A if there's less friction here? Okay, so that would be, let me be a little more coherent now. Part B, if the static friction, kinetic friction, what is the acceleration of A if mu sub K? Block C is removed. All right, so for part B, we're saying block C is suddenly lifted off if mass of C is removed and the coefficient of kinetic friction equals 0.14. What is the acceleration of block B, block A, I should say? What is the acceleration of block A? That's the $sign. All right, so let me kind of fast track this. All right, so my new X-force inventory for block A, there is no X-force inventory for B, but if I look at block A, and again, I'm fast tracking this a bit, there's no more mass C. So I have minus Fs plus T equals mass of block A times A. That's not equal to 0. A is not equal to 0. So the acceleration of block A is going to be the same as the acceleration of block B. So let's just call it A. So here's my X-force inventory. I have minus Fs plus T equals, I didn't say anything different here. So here's my X-force inventory. Having said all this, minus mu sub K times F sub N plus T equals mass of A times A. A is not equal to acceleration. I know the normal force. So again, in the interest of compressing time, I know the normal force. I think you know the normal force is just going to be the mass of A times G. So I'm sidestepping the Y force inventory because I think you can maybe kind of see that, yeah, this is the normal force. Okay, plus T equals MA. So that's it. That's my X force inventory, which also kind of included the Y force inventory. I'm going to highlight that in yellow. Done with the inventories for block A. Here's the inventories for block B. The Y force inventory for block B, is as follows. I have the sum of all those Y forces is minus T plus MBG equals MBA. Just again, because I have the acceleration of block A is the same as the acceleration of block B. Let's just call it A. And that's it. All right, so I have these two equations now. This is the result of my inventory for block B. This, once again, is my inventory for block A. Let's solve for A. Yes, we can do that. Okay. 19. Solve for A. Solve for A from number 15 and number 17. And let me just finish out for myself, just to make sure I'm not making any more mistakes, since I've made a few. Acceleration for me is minus mu sub k m a g plus mbg equals ma plus mb times a. So when I solve for acceleration, minus mu sub k, which is now 0.14, minus 0.14 times MAG. MAG for me is 47. That number's just sitting there. Plus MBG. MBG is just the weight of B. That's 22. Okay. Divided by the mass of A. So I have to go through that conversion. Divided by 47 plus 22. Okay. And I get A equals 2.19 meters per second squared. So at this point, kind of went over 10, which I try not to do. This is the answer to part B. I have the answer to part A. So at this point, that's good for me. I believe, again, all of these quizzes are open until 5 o'clock. So you should be good to go. If you let me know if you have any questions. You just
FS. So you had to use FK for it. So just it's the same number for C as B.
Oh, okay. Then
that's pretty good, Ty. But Levi, is that what you're saying? Does your downforce exceed FS?
Yes, it does.
So then Ty's right. If you exceed FS, then your answer to B is just going to be your kinetic friction value.
Okay, then we're all good then.
That's good. That's very valuable assist, Ty.
Thank you.
All right, you guys. So again,